All right, I put this website, this applet on my website, so you can try this on your own. So up here controls the charge that I'm going to put on the board here. So I've got a charge, a positive charge, so they're going to show up in red. So here is a point charge. Okay, so that's a charge of +1, and you can see the red lines are the equipotential lines, and the white lines are our field lines. So if I reset it and I move it up to like a level 6, you can see that there are many, many more white field lines to represent the strength of the charge. So as the applet follows along with the rules, the more field lines you draw, the stronger it is. And you can see the equipotential lines are drawn in a darker or thicker font to indicate that it's stronger that way. Okay, so that's what the point source looks like. And if I do a negative charge, it looks the exact same. There's no arrowheads on here, so it doesn't have the arrowheads shown. But other than that, it does show the interaction. So let's take a look at two. Let's go with a positive and a positive charge here. So we'll put a positive charge there, a positive charge there. And you can see the field lines, the way they interact or repel each other and push away. And you can see that figure 8 notation around the equipotential lines here. You can see that there are some rings, but the ones, you can see that figure 8, and if we were to zoom out further, you see how that outside ring is becoming more and more circular to become a point charge. So if I reset and try to do them really close together, you can see there are 2 point charges side by side, are really close together, and it's hard to tell the difference between that picture and that picture. So they both, this is emphasizing that when the 2 charges are close together and we zoom out, it starts to take on that look of a single charge. So if I do, let's do a +2 charge and a -2 charge, equal charges. So now you can see how that looping works, and you can see the equipotential lines get a little bit funky when we start changing the charge. So that's why you're never really responsible for drawing them. It's the field lines I'm more interested in, the solid white lines. So you can see how they interact and how they loop. Now I'm going to reset that one. I'm going to do the exact same one again, except really close together to emphasize the point that, nope, that doesn't really show what I wanted to show, but I wanted to show that it does look like a point charge. So maybe I got to jump it up a little bit. Let's go to an 8 and a -8. There we go. And it starts to see how these lines start to head off and create that star pattern. So essentially those 2 point charges, again, doesn't matter whether they're positive or negative, show up as being a point charge. All right, so you can adjust this, you can play with this a little bit, and you can see you can add 3 charges to see how they interact with each other. I'm only going to ask you to be responsible for drawing the 2 point charges and just talking about how they work or interact with each other. All right, as far as that goes, I'm trying to think if there's anything else I wanted to demonstrate with this, but please go ahead, try the website out and try some of the different combinations there, but you can get a feel for those white lines are the field lines, so we would have some tangential force here. And maybe what I'll do is I'm going to create one and I'm going to import it into the diagram or into my note, and I can draw some pictures to it. So let's do something that looks like that, and we're going to move back to the notes for a second. So I did import a picture here that you're seeing on the applet, and I just want to show or emphasize, and maybe the blue will show up better here, that if we had a charged particle here and we were using Coulomb's law, it would calculate the force, but the force would be, again, tangential to the field line that's drawn. So it doesn't matter which field line I'm on. Tangential just means that it's touching at one little point, and that would show you the direction of force. All right, so that's what it looks like in a little bit more accurate form with the applet. It does a fairly decent job for that. Okay. Now I've had people in the past ask, well, why is it tangential? So the reason Fe is tangential. So to keep it simple, if this is my positive charge, so there's my positive charge, there's my negative charge, and we're looking at some charged element right here. So I'm just going to call that C, charge A and B. So what we have is we have a force of, let's say, let's make C positive, just for argument's sake. It doesn't really matter what we pick. So if that's the case, we would have a force of repulsion. So the force between AC. All right. There would be a force of attraction right here, force BC. And if we were then to take our two vectors there and add them, there's my force AC. This is my force BC. Then the resulting vector, or the resulting force, would be at a point tangential. So it depends on where exactly we are talking. So if I go back to the diagram that what I pasted in here, so for example, this one right here, if there was that force to attraction from that point, or sorry, repulsion and attraction, that resulting tangent, and of course it's not to scale, okay, that would be the direction of the resultant that it's being pushed, and it continually changes. So as the particle moves in space, that force and all the magnitudes and the angles are changing. So we're only ever interested at one point in time when we're looking at or doing any calculations. Okay, so moving along, and if you want any clarification, again, make sure tomorrow you do ask, and I think I skipped a slide on you. So let's go back. What happens if we have an unequal opposite charge? So if you can grab, you're gonna have to redraw one of these circles, I apologize. Okay, in this case size will matter, so I'm gonna make that one negative, that one positive, for no real reason other than that's what I've decided to go with. What happens is you're gonna have less equipotential lines connecting to that negative. So we are going to have a line that looks like that, there, coming in perpendicular. And what happens is that negative charge loses the ability to kind of pull in those field lines from the larger charge. So that positive charge kind of takes over the overall diagram here. So that smaller negative charge has less and less influence on the field lines coming out of the larger negative charge. Okay, and it still becomes sort of that star pattern as you zoom out. So again, you're going to end up with the larger charge has more field lines. Charge has more field lines. Okay, and the smaller charge has less influence. On the large charges field lines. Large charges field lines. All right. So there we go. I think I got that, all the slides filled in for you. Okay. So zooming ahead here. So again, make sure you try that out. So what happens if we have parallel oppositely charged plates? So now it's similar to, if you think back when we talked about bar magnets in grade 11, similar idea here. And we're talking about drawing the field lines. So inside, it is what you'd call simple to draw, because the field lines are going to go straight across. Okay. Inside, down the middle, we have our equipotential line. So that's the red equipotential line. And then at the end of these parallel plates, what will happen is the field lines are going to balloon out a bit. All right, similar to that bar magnet when we did it in grade 11 course, and you get these magnetic field lines that are at the outside edge, and we call that edge effect. So if usually the majority of the goal is the magnetic or the electric field inside the plates. So this is usually our focal point. However, when we have this set up in an application in the real world, we have to be aware of these edge effects because they do influence or they do create electric fields. So it is important to remember they're there. They're usually not desirable. Usually that's not the whole goal when we have our parallel plates. Okay. Now down here I have some comments which you can see. And I'm just going to bring that screen back just so I can go through it point at a time so you can follow where I am. So a couple of properties with these plates. The electric field strength in the region outside the parallel plates is 0, except for some slight bulging or those edge effects I was talking about. All right, so the region outside the parallel plates, there is no electric field, except for that edge effect. Electric field is constant everywhere inside the plate, so it doesn't matter where you are within the plate itself, okay? So if you're here, or here, 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 doesn't matter where you are, that field strength is the same. The field lines are straight, they're equally spaced, perpendicular to the plates. Very similar to the bar magnets that are parallel to each other. Magnitude of the electric field at any point between the plates depends only on the magnitude of the charge. So field strength depends only on the magnitude of the charge of each plate. That's the only thing that matters. You'll notice that it doesn't say anything about distance between the plates, okay? It is only the magnitude of the charge. So they could be 2 centimeters apart, they could be 2 meters apart. The last one, electric field strength, E, okay, I've been using that notation, is directly proportional to the charge on each plate and does not depend on the distance between the plates, which I just inferred from the third one there. Okay, so there we go. There's some of the properties when we're dealing with 2 plates, so 2 metal plates. They have an electric charge, and the result then is an electric field. Those are the 4 properties that exist for that particular situation. All right, so let's talk about the single conductor then. So with the single conductor, typically, if you do an end view here of my conductor, typically if you are looking at this from an electrical standpoint, you have your wire in the middle. So we have a wire. And then on the outside edge of it, you have your rubber coating or your insulator. So make sure that you don't get electrocuted when you grab live electrical wires. Okay? The insulator contains the electric field and keeps other electric fields out. Okay? So it reduces the influence of other electrical fields that are created so that when you have your DVD player on, the electrical field created by the wires running electricity don't influence the other components that are working. So the insulator. Maybe I'm simplifying it, I know, for people who are watching this with a little bit stronger understanding. I am simplifying it, but I'm getting to the point where you understand why we do certain things. So the insulator helps contain the electric field. And keeps other fields out. Fields out. All right. Now the field lines would be perpendicular to the conductor. So that means this conductor, all the field lines going to that conductor would be perpendicular. So this is in a straight wire. So if we didn't have an insulator, all these field lines would be perpendicular to that insulator in terms of the electric field. So normally this is where the lesson would have ended. There is 2 more videos, I believe, or will be maybe, and it's on electric field strength. So this was just an introductory topic. So if you're working your way through and you know you already have enough work to keep you busy tomorrow, you can cut it off here and continue. If you are needing to continue through, you need you're caught up and got all your work finished up, then you are going to have to continue on through the videos. There's really no homework associated with this section except for maybe some quick sketches. It's the next part that gives you the mathematical component. So I do apologize for the length, but it's the background information that's important. So anyhow, we'll see you in the next video.